All right, thank you. And thanks to the organizers. I'm looking forward to the week. Once I get through my lectures, then I'll look forward to everything else. So my goal is to talk about a series of conjectures that are about the geometry of periodic or pre-periodic points for endomorphisms of projective space. And I'll talk about what's known for at least some of those conjectures. I won't have time to go through, there's a lot of work that's been done around them, as you will see, and I won't have time to go into detail in all cases, but my hope is that in this lecture, which is 1 hour, I will describe what's called the dynamical Manin-Mumford conjecture and what's known about that. And then in lecture 2, it will be more focused on, or maybe exclusively focused on, not just one map, but families of maps, similar to what Antoine was telling us about sort of extending statements about one dynamical system to statements about families of dynamical systems. So that will be the focus of lecture 2. And in lecture 3, I'd like to do one example and try to explain really what goes into the proofs, which I consider illustrative of how the proofs of all of the cases that we know, they all follow a somewhat similar strategy or outline, as similar ingredients that go into the proofs, including everything that Antoine mentioned to the very end of his lecture and the work of Yuan and Zhang. So there's a lot of machinery there that I won't have time to get into. But anyways, let me begin with a conjecture that was first posed by Shouwu Zhang around the year 2000. I guess it appears in a publication from 2006. So let me go ahead and make a statement. So let's see. Conjecture. All right, so it's a 2006 publication is where the question appears. But I think it was formulated before that, and he was working on these things in the 1990s. The version that I'm going to state has been reformulated and appears in an article of Gioka and Tucker that I think was published in 2021. Now, the setting that you can more or less keep in mind throughout my talks is endomorphisms of projective space itself. So I'm working on projective space. Everything will be stated over the field of complex numbers until I start discussing proof methods, but over the complex numbers. So of course, what are these morphisms? Oh, maybe I should say, of degree strictly bigger than 1. So I'm not dealing with the automorphisms of projective space. So as Antoine mentioned, what are these? These are just expressed as an n+1 tuple of homogeneous polynomials in n+1 variables, each of degree d. And to be a morphism, of course, we must assume that there are no common zeros. So the dynamics of these, of course, many of you have studied them in great detail. Already the case of dimension 1 has highly non-trivial dynamics. The following statement, though, that I'm going to make is really only interesting when n is at least 2, as you will see. So here's the statement. Although I'm going to state it slightly more generally in the setting that Antoine discussed, actually. So let me just assume that Y, which you can think of as projective space, is a smooth, I'll assume smooth for the statement, projective algebraic variety defined over C, and assume that F is a morphism from Y to Y, which is polarizable. Which means, as Antoine wrote in his lecture, so i.e., that there exists an ample line bundle L on Y, so that when you pull it back by F, it's equivalent to taking a power of this line bundle. And specifically, well, he wrote it arithmetically. He had Q times L. Anyways, a tensor power of L to some power. He called it Q. Actually, let's call it D, because I said degree over there, D. So D for integer D bigger than 1. So this is the meaning of polarizable. And again, before I go on, the key example you should have in mind is where Y is projective space, where L is just O of 1. You pull back F by a morphism of degree D, and you get the line bundle O of D. Okay? So you can forget about that general setting and just think about this. Let me further remark now before I make the statement, just one remark after another. It was observed, I guess, formally by Fakhrudin roughly 20 years ago or so, or I don't remember when this paper came out, maybe less, that if you have a polarizable endomorphism, you can always return to this setting because you can take a power of this line bundle, you can use it to embed your Y into a projective space. Of course, it's a projective variety. I can use the particular L or power of it to embed Y into a projective space, and then one can extend the F to a morphism of projective space. So just remark, one can then, there exists an embedding of Y into a projective space using a power of L so that the F you have here will extend to a morphism of projective space. I mean, one can extend it as a rational map, but in fact, if you set it up right, you can do it so it's actually a regular map on projective space. So there's really no loss of generality in thinking about projective space itself. Okay. These are just invariant subvarieties for morphisms of Pn. Okay, so going on, what is the statement? So what we're interested in understanding is the geometry of the periodic or of the pre-periodic points. And the conjecture is that if you take some irreducible subvariety of Y, and if it contains a Zariski dense set of pre-periodic points, I'll say a word about that, with a Zariski dense set of pre-periodic points for F, then X is something. All right, so, no, this one. Can you do two at the same time? No. I guess I better just go all the way up to the top. Then X is something. So the goal is to figure out what that X should be, which subvarieties have lots of periodic or pre-periodic points. And before I go on, let me emphasize that really the X you should think of is just start with any collection, any infinite set of periodic or pre-periodic points, and what is X? The smallest algebraic variety containing it. Its Zariski closure is what you should think of, an irreducible component of its Zariski closure. Okay, so what should X be? So the original conjecture, so this is continuing, is that X itself should be pre-periodic for F. That if it has lots of these pre-periodic points, we expect X itself to be pre-periodic. And in most of the cases that we know about, that will be true. But there are some exceptions. And so there was a follow-up paper of Gioka, Tucker, and Zhang together, and then to try to correct the conjecture, but I'm going to follow the version of Gioka and Tucker that I mentioned there. So roughly speaking, the conclusion is that it may not be pre-periodic for F itself, but it will be pre-periodic for something related to F, something that perhaps commutes with F. So I'm going to write it this way: F is, or X, either X is pre-periodic or X is pre-periodic for an endomorphism that commutes with perhaps an iterate of F. And let me be more precise. More precisely, they propose the following conclusion, that there exists some sort of intermediate algebraic variety, which I'm going to call X prime. So there exists some X prime, which might be larger than X, such that three conditions are satisfied that, or maybe more than three. I want X prime itself to be invariant for F, or for an iterate of F, so that X prime is invariant for some iterate of F, for some n. Oh, sorry. The whole point was this endomorphism. So there exists some intermediate X prime and a polarizable endomorphism. Okay, so itself, G is also polarizable of X prime, so that that particular iterate commutes with G on X prime. And finally, the key point is that X is pre-periodic for G. So an X might not be pre-periodic for F, but it'll be pre-periodic for something related to F. And possibly related in this way. This is just a conjecture. So this is a starting point. But again, the assumption is, if X is the closure of the Zariski closure of some collection of pre-periodic points, then X should be pre-periodic itself. Is the idea. All right, so now there's a lot to say about this conjecture, but I want to say a little more to help understand it. So let me say something about the history. Yeah.
Do they say that the polarization is the same, or they're vague about this?
So they actually say the polarization is the same, and that G extends to the given Y. I have weakened, so actually I'm glad you asked this, because I have not formulated it exactly the same way that Gyoka and Tucker do. I have weakened the conclusion very slightly, just in case the polarization is different. I don't want to require that G extends to Y. I don't know any examples where that could fail. As far as I know, anytime this happens, they commute after all, so they should have the same sets of polarizations, but if there's something funny that happens, I don't know. Yeah?
This one is correct for abelian variety.
Yes, this one is correct for abelian variety, so I will say something about that. Yeah. I do not. That's right. So I would expect that probably G actually extends to Y. And this holds in the settings that we know. The stronger version holds in the settings. One can be much more precise and say what the exact exceptions are, and I'll tell you what we know. But I am cautious, and so I wasn't. They were cautious, and I'm writing. It's their conjecture, after all, I suppose, not mine. So I was trying to be actually even more cautious than they were, just to be careful. But the only exceptions we know come from products of lattice maps, or on an elliptic. Come from products of elliptic curves with complex multiplication, or even abelian surfaces with complex multiplication. It's not just a one-dimensional phenomenon. Okay, so of course I'm talking about abelian varieties and elliptic curves all of a sudden, so let me just say again. So this conjecture, I said, did I write this down? No. Dynamical Manin-Mumford. So it has this name, dynamical Manin-Mumford, and so I will refer to it as DMM for those letters. Now, why is it called that? It's because Shou-Wu was thinking about the original Manin-Mumford conjecture. Yes? I'm sorry, if what? G is polarizable. It has to have degree. Yes, my definition here. Yes, yes, it includes the fact that the degree is bigger than 1. Correct. Correct. Yes. But you're absolutely right. G could be the identity, and that will commute with any endomorphism. Yeah. Right, then that's included in this conclusion. So G could be F, in which case it would go back to the initial statement that X is actually pre-periodic. Right, because the point is I want it to be pre-periodic for something non-trivial related to G. (1983), I think. So let me state a fairly strong version, maybe not the original version of the Munn and Mumford conjecture, but what Renaud proved is that suppose A is an abelian variety. Let's work over C. And suppose that X inside A is irreducible algebraic subvariety containing a Zariski dense set of torsion points for this group variety A. Then the conclusion there is that X knows about the group structure of A. In other words, X is a subgroup of A, or perhaps a translate of a subgroup by a torsion element. So then X is a, let's say, A torsion translate of a subgroup. Which one is this? This is the middle one, and I can put it in the middle here. Okay. All right, so what's the point? So actually, Antoine mentioned in his talk, as an example of a polarized endomorphism, you could take an abelian variety and take something like multiplication by 2 on the abelian variety. So of course, the abelian variety is a group. In fact, for any integer n, let's say any integer n, of course, we can define a morphism from the abelian variety to itself. So the 2 case just corresponds to taking a point and adding it to itself, multiplication by 2. You could do multiplication by any integer. And if you take L to be both ample and what we call a symmetric line bundle on your abelian variety, so symmetric means that if you take the endomorphism, which is -1, in order to send P to its additive inverse, and you pull back, L by -1, you get L, not L inverse. Okay. So symmetric means that L is invariant under taking the additive inverse of the point. So that's symmetric. Sorry, that was the definition of symmetric. So if you do that, and then you pull back n, what's called the theorem of the cube for abelian varieties tells you that if you then pull back by n, you get L to the power n squared for any n. Sorry, can you see that? That's a squared. It's kind of small. And maybe I should have raised this up a little bit more, not be in the shadow. There we go. And so in particular, if n is, well, at least 2 in absolute value, this is a polarized endomorphism. So this is polarized or polarizable, polarized by that particular L, for as long as the absolute value of n is at least 2. So this comes from what's called the theorem of the cube, if you haven't studied abelian varieties before. For a symmetric, specifically for a symmetric line bundle. And these exist, these ample and symmetric line bundles, of course, exist. A is it's an abelian variety in particular, it's projective. And then you can set it up so you can build symmetric line bundles on it. Okay, and so in particular, the connection between this and this was, I guess, Shouwu was observing that one can view endomorphisms of projective space on the same footing that one might view endomorphisms of abelian varieties, at least certain ones, when the degree is bigger than 1 on the projective space and when it's, say, polarized on the abelian variety. Note that the pre-periodic points for, the set of pre-periodic points for this endomorphism n, as long, again, let me assume that the absolute value of n is at least 2. The set of pre-periodic points, that's what this notation is the same thing as the torsion points. Okay? You take a point on the abelian variety, if you multiply by n repeatedly and it eventually cycles, that tells you it's torsion, and vice versa. You have only finitely many multiples to work with, so it has to be pre-periodic. Okay. So the pre-periodic points are exactly the torsion points. And so this is the parallel, at least to put this, to try to compare the two statements, at least the hypotheses of the statements. I do want to make a comment. It's not obvious from the way I've formulated this dynamical conjecture. It's supposed to be a generalization of the Manin-Mumford conjecture. It should imply the Manin-Mumford conjecture, and that it should have that is to say, as a special case. So I want to say a few words about why that's true, because people don't usually talk about that. And so actually, there are a couple things I should mention. So I was told that for these lecture series, we should be writing up lecture notes and that they will be published. In fact, I have typed up lecture notes, but if you're close, you can see that my handwriting is still all over it. So it's not quite ready for public consumption, but I might be able to put a version of these lecture notes on my webpage tonight or something, just so that tomorrow, if you wish, you could follow along the typed version. Anyway, some version that might be not correct might be available. In any case, what I wanted to say is that I've got a few extra examples in here that I won't have time to talk about, which is why I want to mention it now. For example, so of course the fact that this is polarized, what was the point? Tells us that we can embed our A into some big projective space in such a way that, let's say, multiplication by 2, for example, will extend to some morphism which restricts to multiplication by 2 on A, okay, whose pre-periodic points on A are precisely the torsion points. Okay, so we can put our abelian variety and the study of the geometry of torsion points into this more general context. Now, people say this a lot, but people rarely write down how to do this and what you get for such an F. So just for fun, I've included one example in the lecture notes where A is an elliptic curve and what formulas you can get. It's not a unique extension, keep in mind. There are many ways to extend to a regular map. So I've included, so you can take an elliptic curve embedded in P2 in the standard way, take multiplication by 2, and it will, in fact, extend to a morphism of P2 that preserves that elliptic curve. So I've included some examples that I won't go. Yes. So in fact, the example that I wrote, so it comes from a paper of Bonifant and Dabija from 20-some years ago, and they actually work it out for an example that will, the same map won't preserve all. They put all the elliptic curves in the same way. They do it in a family, and so the answer is yes. So they do it in a family, and so one gets a rational map that works for all of them. But if you want it to be regular on each individual one, I think you have to. It depends on the choice. Yeah, you only have one elliptic curve that will be invariant for that particular, if you want it to be regular. Yeah.
One of the things we get from Lonnie Mumford is that simple abelian varieties don't have positive dimensional invariant subvarieties. And I was wondering if there's a notion of like dynamically simple varieties where you would have like an infinite endomorphism ring but geometric exceptions to the existence of positive dimensional invariant subvarieties.
Wait. So in the setting of projective space, for example? Sorry.
So other than in the abelian setting where we have the simple abelian varieties,
Okay.
the geometric reasons cannot admit.
Invariant, yeah.
Are there examples of like dynamically simple?
Yeah, so actually they're hard to write down. I mean, it's hard to come by, but in one of Falk-Rudin's papers, not the one that I mentioned, but another one, he proves that, yeah, he gives an argument about why the generic one will not have invariant subvarieties except for points and the total space.
But still, so sorry, the generic map.
The generic map, which sounds formal and it's generic in the sense of function fields, however, as Max and I were discussing, yeah, so if you do some certain kind of specialization argument, that would mean, in fact, over C, the generic, meaning there's some dense collection of maps that do not have invariant subvarieties. But I mean, it's not totally obvious, but yeah, if you write it down, I guess where all the coefficients are independent from one another. You have pi, you have e, you have a bunch of different transcendental coefficients that are all like sort of maximally independent from one another. Is that, did you make a comment?
Except that you don't know that P and R.
Yeah, except that we have not proved that those are actually independent, right? But let's pretend we have. So let's just call them pi 1, pi 2, pi 3, pi 4, et cetera. And whatever they are, we're certain they exist. And so, yeah, so one would have to be sort of maximally transcendental. Right, so I don't know how to write down any such example to guarantee. It's actually quite hard to write down explicit examples that don't have invariant subvarieties to really be able to prove that there's no invariant subvariety. But they seem to be the generic situation. Okay. By the way, yeah, so I wanted to sketch why this is, in fact, a special case. So just a few words about that. So I've already given you the initial setup. So this is a sketch. That's what I'm going to write. And by the way, the following argument appears in an article of Bogomolov from 1980. And so what remains to show? So you start, in order to prove Manin-Mumford, if you know the dynamical version, again, so you start with some abelian variety, and let's take the multiplication by 2 endomorphism. And so then what do we know? We have, of course, we're thinking of our A, maybe, well, A is now, we have this polarized endomorphism. I've written in this general form instead of passing to projective space. And I have some X inside here with its dense set, Zariski dense set of torsion points. And the conjecture, the dynamical version tells me that there's some intermediate X prime, which is invariant for this N, or pre-periodic for this particular endomorphism, but actually pre-periodic for some other endomorphism. That's invariant for some other endomorphism, saying that X is pre-periodic for G. Okay. So just for simplicity, let me assume that G equals F. Okay. In other words, let me just assume for the moment that X is actually pre-periodic for G. Okay, so DMM implies, from DMM, assume G equals F. So X is in fact pre-periodic for F. And by passing to an iterate, let me assume that it's actually periodic or even fixed for simplicity. In fact, assume I've passed to an iterate. Let's just go as far as saying that F is actually fixed for, X is fixed for F. Okay, so let's just understand briefly why does that imply, what do I want to show? I want to show that X is a group or a translate of a group. Okay, so this is all you get from the dynamical version. And so Bogomolov observed the following. So notice, so of course, multiplication by n, abelian variety, this is just a complex torus. Multiplication by n is a covering transformation. It's just a covering map. So by topology, we have this covering map. We know that there's some group of deck transformations for this covering. And what are those deck transformations? They're just translations on the abelian variety. Okay, so the covering transformations are just translations on your torus. And X is invariant for that covering map. So X must also be invariant for some subgroup of the covering of the deck transformations. So this argument tells us, X is in fact invariant. So I'm really using the group structure here. X is invariant for a finite group of A, or translations of A, which is really a subgroup of A itself. And how big is that group? Well, the size of the group has to be related to the degree of this transformation. So, of course, the topological degree here is what? Is n to the power 2 times the dimension of the abelian variety. That's the topological degree of this covering transformation. When you restrict to something of dimension, say, k, then it will have the same, it'll grow the same way. It's a polarized endomorphism. The topological degree will always be the polarization degree to the power, which is the degree. So it's n to the 2, say, I'm going to call it k, where k is the dimension of X. Okay, so this is a general fact that if you have a polarized endomorphism of polarization degree q, then the topological degree will be q to the power k if k is the dimension. Okay, so X is invariant for this finite group of translations of that size. And so what he considers is a particular subgroup of A, which then corresponds to all the translations that preserve X. So this is a particular finite set of them, but let's look at the set of, let me use another board so I have space. I can erase there. Oh, I can also use these. Does it show on the camera and everything? But maybe not here. If Stefan, if you can't see it, I don't know. No, you'll have to watch on the TV then. Okay, if that even shows. Okay, so just to continue there. So consider what I'll call B for Bogomolov. Say B is the set of all what elements of A which leave X invariant under translation. Okay. So this B is a subgroup, notice. So this is a group. It's also an algebraic variety. It's an algebraic subgroup. Right? If you take an A and you take a B, it's invariant under A plus B. So A plus B would still be in B. Okay, so this is a group, and I've just said here that it contains as a subgroup this finite group of size n to the 2k. In particular, if you look at the subset in here, which consists now of, say, torsion elements of order n, inside this group, there are at least n to the 2k of them. Just from the fact that I know I have this translation subgroup of size n to the 2k. This is a covering map. They correspond to preimages of a particular element. That's the size of that, so that tells me this. All right, so this subgroup B, it might be finite, it might be not, but it has cardinality at least that. Okay. And here's what Bogomolov does. He says, well, remember, it's not just that X is invariant under F itself, it's also invariant under all the iterates of F. So I could repeat this counting for all the iterates of f, in other words, the powers of n. Oh, n here was 2, but I guess it doesn't matter. Anyways, maybe it doesn't matter. N can be n, but as long as n is at least 2. I'll just write n equals 2. So in your mind, I don't remember if I don't think it matters anywhere, but just n has to be at least 2, we can take it to be equal to 2. So you can repeat the same argument for exactly the same b, which tells us that if you take powers of n, so the iterates of your map f, that this is growing. Like this, okay? So look at these particular powers, I know that this grows. And then we can pass to some kind of limit, take the union of all of these things, and what does that imply? It tells us B, remember, is an algebraic subvariety. It's also a group. It tells us that it's positive dimensional, and in fact, B itself must have dimension K for counting reasons. B is a group, so we know a lot about the structure of subgroups of an abelian variety. So this tells us that the dimension of B has to be at least K. In fact, equal to K at the end of the day, is what we learned. I suppose technically at least K, because I put a greater than or equal to symbol. But then the point is what? The point was just that now I want to compare X and B. Now, B might not be irreducible. B might have multiple components. But let's just look, for example, at the component which contains the 0. So let's just say connected component containing the identity element, the 0 of the group. Let's call that B naught. Now you could just, for example, define a map from, how did I put it in my notes? If you want to build now an isomorphism between B naught and X is the point. What did I write? I don't even know what I wrote. Where did I write it? Oh, I see. I wrote B naught. I wrote it as, you can define a map, B naught to X. You fix any base point, choose any X naught in your X, and send an element B to X naught plus B. So this has to be an X by the definition here. And so dimension count would tell you that. And because of the dimension, that it has to actually, they will be equal. They're both irreducible and they have the same dimension. Okay. So the upshot is that X is a translate of B naught. Okay. They have to be an isomorphism. Okay. So that tells you that that was the conclusion, that X is in fact a group itself, or a torsion translate of a group. One knows that it would be a torsion translate of group because, well, I guess because of the fact that there are, I mean, it's a subgroup, and there is a Zariski dense set of torsion points in it, so it would have to be a torsion translate as opposed to a non-torsion translate, in which case you'd be messed up. Yes, and yeah, good point. I could just take that to be a torsion point because I already know there are lots of them. Thank you, that helps. That clarifies. Yes, take X naught to be a torsion point itself. Okay. And that gives us
So you assume G is equal to F, is it a big deal?
Okay, right. So I did make that assumption. So it's not a big deal at all. In fact, if you step back and look at this argument, if I were to replace multiplication by n with G, at every step, the first observation is that this is invariant for G, well, this is invariant for F, or for a multiple of F. So that would tell me that this is a subgroup by the argument I just went through. So this guy has to be a subgroup. It's a sub-abelian variety, or a torsion translate of one. And then G would be an endomorphism of it. Therefore, G is itself a covering transformation, and it's polarized, and so it has its own polarization degree. One applies then this same argument for G and realizes, actually I can just replace n squared everywhere with Q, the polarization degree of Q, and the same argument actually goes through exactly the same. As long as I know here that the thing I started with was a subset of A. Yeah? I was using the fact that I have a covering space. I have a covering space of topological degree n to the 2g. And so it's I mean, the deck transformations for that cover are translations.
At the level of A, I understand.
But X is invariant, so I'm assuming F is actually fixed by, sorry, F is N. So I was assuming X was fixed by that covering transformation. And so I was just looking at, so if I think of it as a covering space, I was just looking at take X, move it by, it has to move by those same deck transformations. It has to move by the same deck transformations. By the way, Bogomolov wrote this argument. This was not his intention. Of course, dynamical Money-Mumford wasn't something discussed at the time. He was actually in the process of proving cases of the Money-Mumford. Notice the dates. Bogomolov wrote this. This is a publication from 1980, which actually I think came from a letter he had written to Serre. You know, the first proof of Money-Mumford came around in 1983. So anyways, he was in the process of proving a special case of the Money-Mumford conjecture. Under some additional hypothesis, if the torsion points in the subgroup satisfy something, then you get that it's a subgroup, and he reduced it to this argument. And this is contained in the proof. It is not a statement that stands alone there, if you look inside his paper. Oh, how am I doing? Yeah.
Where I was confused is, how do you know that G extends to A?
I don't, and I don't need it. So what I do know is the following. G leaves us some X prime invariant. And so, so F leaves, thank you. F leaves X, where did that come from? Who said that? Thank you, Thomas. Sorry, not only G, F leaves X prime invariant. I do the same argument to say X prime is a subgroup. Now I have an endomorphism of an abelian variety. Thank you, I knew it was there somewhere. Okay? Yeah, thank you. It's at left invariant by G and by F. Thank you. Yes. Oh.
Endomorphisms of abelian variety. Translations composed with.
Our translations composed with an isogeny, and so right. So we have to use some extra facts about abelian varieties and complex tori. There's a little bit of extra background input that goes into, sorry, I guess, to fully understand it.
So now, I have a very nice question because I'm not working in this field.
Yeah.
Are there so many examples? I mean, if you assume that, for instance, Y is positive quadral dimension, I don't see a single example.
Right.
So, the only question.
Yeah, so as of now, yeah, so there are abelian varieties, right? There are, like, you could take a rational curve inside you can embed some rational curve inside some projective space. You know, the full list of examples is still unclear, unknown. I
think if you work with projective space, everybody.
Yeah, I mean, right. We can just assume that it's projection space. But the thing is we would like to know a complete classification. And there is some work out there that's been done, for example, by Deqi Zhang and various co-authors, saying what type of algebraic variety does it have to be that actually admit polarizable endomorphisms, or a slightly more general setting of what are called amplified endomorphisms. And so there is a whole study on, if they're, properties of these algebraic varieties that I don't know anything about.
So, for instance, if I assume that Picard is Z.
Oh, would that be enough? I don't think so. Oh, I don't know anything in this direction. I doubt it.
No, Picard is P1 times P1. Yeah.
Are you saying, but if you assume, yeah, probably not. Just extend to Pn. But no, I don't know, and I don't think anyone knows a complete list of what these can be or what they are, which is unsatisfying.
So I have a second question. If you're interested in positive quadral dimension, can we do what is? I mean, can you make a version of this conjecture for
Whoops. One could make a version of this conjecture in many different settings. And there are even settings, yes, where you're thinking of, say, an automorphism of some projective variety, that there are results that are, that are known, and one can generalize this in many different directions. So let me just say that. I'm sure, like for, what am I doing? I want the other one to go up. Was it this one? Yes, all right. It's hard to think and move the boards at the same time. Just stop asking me questions while I'm moving the board. Yeah. Yeah.
Before you raise a conjecture, there is another direction which is not so easy.
Oh, if you start with something pre-periodic, then it's guaranteed to have a Zariski dense set of pre-periodic points.
Also,
Now,
also in the more precise case, you have FG, blah, blah, blah. That's the second.
yes, absolutely, because again, it's polarized, right? So if I'm assuming that G is polarized, and so it would be the same statement, right? I start with anything that's polarized, and if you have a subvariety which is pre-periodic for a polarized endomorphism, now stated in this generality, and working over a very general class of fields, I don't remember exactly what fields he was working over, Fakhrudin states this result that there is always a Zariski dense set. Now over C, and working, for example, in projective space, one can work with, or even subvarieties of it, one can work with those canonical measures that you mentioned in your talk and use complex analytic properties of those invariant measures that are finite energy, that are, have bounded potentials, and use that fact to plus the existence of the dense set of repelling points inside the supports of those measures. This is building on a lot of theorems over a number of years to get property, to use complex analytic arguments to get that Zariski density. So it really is an if and only if statement, and I have not done justice to those references and the background. So just so everybody knows, it really is an if and only if statement. Yeah, thanks for that question. Okay, so I wanted to say a few words. So I guess my official starting time was 20 after, although I suppose we started a couple minutes late. But I do want to say a few words about the cases that are known. The only thing that I've mentioned is the case of abelian varieties. And the reality is very little is known. And maybe the conjecture is false. So the first dynamical case that was not abelian varieties is a theorem that was proved, let's see, in a series of papers. So it starts with actually two papers of Gyoka, Nguyen, and Yi, but was completed, I guess, recently in a short follow-up work with Mavraki, Schmidt, and Wilms. If I have a moment, I'll say what's in all the various references, but there are two. So this is times two, this set of authors. And they handled the case, in fact, the only setting where it's complete, aside from abelian varieties, is the case of endomorphisms of a product of P1s, okay? Which, after you pass to an iterate, is really just a product map. So let's just assume that F is a product map. Now, to be polarizable means that the degrees of all of the components of each of the product pieces is the same. And I'm assuming, I'll just call that D, this degree D bigger than 1, so that would also be its polarization degree. Okay, so this is a polarized endomorphism, so it embeds into some larger projective space. If you wish, you could think of it as an endomorphism on a big projective space, or you could just work with it here on P1 to the n. And what they proved is, so if, is the same statement, is an irreducible algebraic variety. Remember, we're working over C here. With a Zariski dense set of pre-periodic points, then actually there's a stronger conclusion. We know exactly when that funny exceptional thing happens. So then X is pre-periodic for F unless special situation, let me not write it out, special case involving lattice maps from elliptic curves with CM. So let me not write it down just for sake of time. There's an exception. I can tell it to you in detail at a break. But the main point is that in this setting, there is a complete understanding that if you take any collection of pre-periodic points, pass to a Zariski closure, that set X would have to be pre-periodic also. Or you get the other conclusion in some special situation. Yeah?
So in their theorem, they need all the FIs to have the same degree?
Actually, no. That just puts it in the context of the dynamical Money-Mumford. Their proof uses it, though, no, I don't remember, to what extent they prove it slightly more generally. I actually don't remember now. Do you know?
So I think when the degrees are not equal, there aren't like interesting pre-periodic.
Maybe that's the point. Yeah.
If you want the degrees of the polynomials to agree, I mean,
In order to even have an invariant subvariety, which is non-trivial, they have to be related, but multiplicative dependence. Okay, but it still allows, of course, for some other examples. Thank you. There would be, if you have some kind of non-trivial that's not just one factor or something with crossed with a periodic point. But yes. Yeah, so in this case, and it goes further, their theorem goes further to give more, a little bit more of a description of what these x's can be. There is not a 100% complete description, but anyways, this conjecture is resolved.
at the end of the day, they prove their conjecture in this system.
Thank you. At the end of the day, they proved DMM in this case. In that version, in a stronger form than what I've written on the board. Yes. That the conjecture that I stated is proved in this case. And that we know that the only times you have to deal with this G comes from a very special situation involving lattice maps for elliptic curves with complex multiplication. Those are the only examples there. Okay. Oh, the DM, I guess I started it here. Okay, but the conclusion was up there. Yeah. So that's one setting, and then there's one other setting, and since the three authors of the other setting happen to be in the room, I had better state it before I run out of time. So there's one other setting where it's known. Oh, maybe it's not good practice to erase the conjecture. I can erase that argument. So was that if X, what did I say, is irreducible subvariety with, okay, let me just go over to here and state a case of the conjecture, which is proved in a recent preprint. By 3 people in this room. Okay, so notice these were products of projective lines, and because they're projective lines and these are products of one-dimensional morphisms, there's a lot of extra machinery that we know about that we can use coming from complex dynamics in dimension 1. And it's not only the one-dimensional complex dynamics, it's also the product structure, which they use in a crucial way. It's not just one-dimensional dynamics, but the fact that this is a product, P1 cross P1 cross P1, is used absolutely crucially in both the proof and in the conclusion to understand what these x's are. Here, the authors work with endomorphisms of the projective plane. And as a starting point, they're able to handle polynomial maps. So which is, I don't know, what do we say, a regular polynomial endomorphism? By which I mean, if you restrict to a certain affine chart, this morphism on projective plane is actually a polynomial endomorphism of A2. Okay, we're working over C here. And so here the subvarieties are, well, points. We're not, the case of a point, there's nothing to show, but we're interested in, say, curves. So suppose X is an algebraic curve which satisfies some hypothesis. What is the hypothesis? Such that if you intersect with that invariant line at infinity, I don't know, well, let me just call it L infinity and say what it is, such that this intersection has what? At least one point which is not pre-periodic to a super, it's not pre-periodic to a super attracting, anyway, there's some hypothesis, has at least one point not pre-super attracting, something like this. Okay, there is a hypothesis. Please ignore the hypothesis. Then X is pre-periodic. Oh, sorry, with the whole point of it. That's blah, blah, blah. With infinitely many pre-periodic points, suppose X is an algebraic curve such that its intersection with the line at infinity and those polynomial coordinates has at least one blah, 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 and X has infinitely many pre-periodic points. The conclusion is that X is, in fact, pre-periodic. None of those weird exceptions. It's polynomial maps, a curve with infinitely many periodic or pre-periodic points, the curve itself is pre-periodic. So that resolves a case of the DMM in dimension 2. And as far as I'm aware, it's the only case that we know which is not sort of fundamentally relying on one-dimensional dynamical techniques. Okay. Now, that's just to emphasize the sad state of affairs for this conjecture that may or may not be true, but it's definitely believed to be true by a number of people, I don't know, including myself. Maybe not believed by everyone, I don't know. But yeah, they're just the tools that we use or that are used in cases we know, such as in this setting, or the tools that are used there in the proof of the Manin-Mumford conjecture. By the way, there are many proofs now of the original Manin-Mumford conjecture, the case of abelian varieties. There are a number of different proofs. Of course, there's Raynaud's. Anyways, there are a lot of different proofs, but all of them start the same way. Let's reduce first to the case of Q bar. So I stated it over the field of complex numbers. It turns out it suffices to prove the result over Q bar by certain specialization arguments, various arguments that are considered standard in that world. And then what's the advantage of that? We have a handful of arithmetic tools that we can use, some of which were mentioned in, or referred to at least, in Antoine's talk. And now I'm out of time, so I don't have time to mention them, but there will be some mention of it in my notes. And certainly in my lectures tomorrow, I will go a little bit into the arithmetic side. This is supposed to be a conference in arithmetic dynamics, so we're supposed to actually say some of the arithmetic stuff. But I wanted to spend this first hour on this statement. So in that case, we have arithmetic tools. We reduce to Q bar. All the proofs go through that as far as I'm aware. And certainly these two proofs as well. The specialization arguments are not so clear in this general dynamical setting. There's work to do to the passage from C to Q bar. Here it's a little more straightforward, where we know a lot more about these types of dynamical systems, how the periodic and pre-periodic points behave in families, because that's what it really boils down to, those specialization arguments. And so that requires some work. But some ingredients are really, a crucial role is played by the two things that Antoine mentioned. So let me just finish by saying canonical height functions. If you assume your map is, say, defined over Q bar, then you can build height functions, as he mentioned in his lecture, and a crucial role is played by those height functions as a tool and the associated metrized line bundles related to those heights. And than the equidistribution theorems that he also mentioned. So here the authors rely on Yuan's equidistribution theorem. These are projective varieties. I think you guys also do, right? You're also relying on Yuan's equidistribution theorem to handle curves. And Zhang's and he also mentioned the fundamental height inequality, which is another ingredient that's often used for these proofs using, it's really the key tool that comes from height theory and intersection. So exactly the stuff that was mentioned in Antoine's lecture, which I don't have time to go into right now, but I'll try to say more about in my lectures tomorrow. Those are important tools for the proofs of any of the cases that we know. Well, there, I'll stop there.
All right, thank you, Laura, and I might need dramatic with the microphone again. It doesn't.
Oh, and now it's on. It's on. He just touched it.
I know.
It's amazing. So we might have time for one quick question before the break. Someone have a... It could be that your question is already going to be answered in part 2. So...
Yeah, this year, well, I don't know, actually it was a preprint from some years ago, but then released this year or something, I don't know, when did you write it? This year? I thought it was something you guys had resolved some time ago and then finally just wrote it up this year. I don't know, oh man, yeah. Anyways, the preprint appeared just in 2024, I think. Yes, it's totally invariant for this endomorphism, right. So that would also, is a characterization of being a polynomial endomorphism. There's a line which is totally invariant. Thank you, yes. Yeah, I was rushing.
You mentioned there are several proofs of the random theorem.
Yes. Can I list them? I could if I worked hard enough. Maybe Bruno could help me out. But we've got, well, there's the Pila-Zanier method. And Hrushevsky has an argument. There's, you think that's it? And then this one, it's just those three?
Well, that's a general method.
And, and then Bogomolov and Zhang. And the Bogomolov, their proof gives yet another proof of the Manin-Mumford, so that's another, yes. The Ulmo and, yeah, sorry, Bogomolov. The Ulmo and Zhang arguments, yeah, also.
And in some sense, Moriwaki has a variant of the Ulmo-Zhang proof because you can prove it
Yes.
without specialization arguments.
Okay, and then Pink and Roessler in their paper also have an argument. So we can come up with all of them. Pink, Richard, and Roessler, R-O-E-S-S. But it's a variant of Hrushevsky's argument, that's right. But it changes though, it's a little different. It doesn't use so much model, maybe it's no model theory at all, I don't know. It was inspired by his argument, but without the model theory. Yeah, and then you kill them. So it is a pretty long list to go through all the details, as well as partial results that had preceded, I know. Okay.
All right, well, in the interest of time, let's thank Laura again for a wonderful talk.